part of this, what we learned about until now. So now it's going to be called a randomized, what Paul was suggesting is a randomized block design. That's the fancy name for this other approach, because basically instead of having 9 people, now we're back to 3 people. These are the people, person 1, person 2, person 3. Each person contributes 3 numbers, that's true, so we still have 9 numbers, but each person contributes not one number, but a block of data. A 3, then a 1, and a 7. Why is it called randomized? Do you think that we give everybody drug number 1 first, followed by drug number 2, followed by drug number 3? That's what it looks like when you look at the data set. But what do you think happens in reality? Do you think you give everybody 1, 2, 3, 1, 2, 3, 1, 2, 3? What makes more sense? No, we can wait 3 months here, wait 3 months. I'm talking about the order of giving them the drug. The fact that we have a washout period goes, that's a separate issue. We need a washout period. But I'm asking you, what about the order we give the drugs? Does it make sense to always give 1, 2, 3, 1, 2, 3, 1, 2, 3? Yes. No, you can't. You can't give it the same. In other words, you can't give the same time. You mean give everybody? 3 people can't take all 3 drugs at the same time. That's first of all. I don't think you meant that. You don't mean take all 3 drugs at the same time. Well, let's say we decide person number 1 is going to be taking drug number 1 today, and at the very same minute, person number 2 is taking drug number 2, and at the same very minute, person 3 is taking drug number 3. The fact that you take it at the same time or a minute later, it's probably a good idea to give it at the same time for practical reasons, and also for maybe the atmospheric pressure has an impact on the data. Who knows, right? So that's not a bad idea. But I'm asking you about the order of giving the drugs. It looks like 1, 2, 3, 1, 2, 3, 1, 2, 3. Do you think you would do that in reality? Well, again, you don't compare them simultaneously. You collect the data, and then you give it to a statistician to analyze the data. You don't have to worry about this got to make a decision right now comparing 1 to 2 to 3. At the end of the day, you have just a set of data. Like originally, we didn't know when we gave the drugs. We just gave, this represents the data. I'm surprised no one's telling me the answer I'm trying to get. It's called a randomized block design. Why is it called randomized? Because we don't give drug number 1, 2, 3, 1, 2, 3, 1, 2, 3. We randomize it. In other words, you say, you're going to get drug 3, 2, 1. You're going to get drug 1, 3, 2. You're going to get 2, 1, 3. Everybody gets a different order. Why would you want to give a different order? And again, it's pulled out of a hat. It's not even done by, you don't even decide. Why would everybody get a different order? Yes? Yeah. Even though we're having a washout period, maybe the washout period not really affected. Maybe once you get better and you feel better, you start acting differently over the next couple of weeks, so it's going to mess up your second drug. So in order to make sure that that doesn't happen, or to minimize that possibility, we basically randomize it. So that was the. So in other words, this is another. So sometimes the point is, and the formula is a little, not the same formula. It's a little bit different. Of course, we have a different concept there. And for example, one of the things that the formula would take into account. Now, we didn't learn about chapter 13 yet, which is correlation. But you would think that there's a correlation between the drugs. The people who do better in drug 1 also do better in drug 2, perhaps. And the people who do worse in drug 3, there may be some kind of a pattern among the results that might help us analyze the data better. So that's something that this formula will take into account. This is the minor part of what I wanted to show you today. Now comes the major part. Anova. Now, till now, and this is the part that you're mostly responsible for the calculation point of view, we've been talking about a one-way Anova because we just want to compare the 3 drugs. And if you made a picture of this, let's make a picture of this. You have drug 1, 2, and 3. You have the change in blood pressure. And in fact, it's really the average change in blood pressure, the mean change in blood pressure. And this group seems, if you take 2, 3, and 4, the average is about 3. So 1, 2, 3. 1, 2, and so you can make a point like here to represent the 3 numbers. 1, 4, and 2, which is about, what is that, 6, 7, 2.3. The average there is about 2.33 around here, and the average for drug number 3 is about 7 point something, which is over here. So if you had to make a line to connect it to make it more visible, the dots, this picture here would basically be a good profile, sometimes called a profile actually, of the experience of taking these 3 drugs for these 3 people. Now, do you think we mixed men and women here? You think these 9 people are like 4 men and 5 women? Well, sometimes that could be the case. But you probably, when you design the experiment, you try to have everybody as similar as possible. The same age, the same race, the same sex, the same the amount of disease. Like you don't want to have people who are mildly sick and people who are very sick because it messes up your data. You want to make sure that the people are as similar as possible. Basically, the experimental error should be as small as possible so that, why would you want to have the experimental error as small as possible? Somebody tell me, besides the common sense reason that you want people to be as similar as possible to do the experiment, can somebody take this a semi-mathematical step ahead? Where in the formula does it make a lot of sense to try to minimize the experimental error? It's a little bit of an abstract question, so let me try to answer it myself so we can finish on time, which is the formula for the F was equal to MSA over MSW. And MSW, if you remember, is the true measure of the experimental error. So if that number is as small as possible, what's going to happen to the F? It's going to get big. And if the F is big, what happens? We end up proving our H0. We end up rejecting our H0 or believing the H1. So actually you get to prove the drugs are truly different. So if you want to maximize the chance of proving that your new invention is really working, you try to get the people as similar as possible to minimize the MSW. But let's say somebody inventing this drug says, you know what? In my experiments with the rats, no offense to anybody here, it turns out that the men did better in drug number, the male rats did better in drug number 3, but the female rats did better in drug number 1. Wasn't that the one drug is better across the board? There seems to be, and the technical term for this is interaction, there seems to be an interaction with sex, meaning that you can't say across the board drug number 1 is the best drug, which in this case drug number 3 is the best drug. You can't say that. It's true for men, but it's not true for women. So basically, how would you, when it comes time to experiment on people, if you believe that biologically there's a connection, how would you set up the experiment so that you can actually test that? How would you modify this whole setup that we have so far so now you can actually test to see if there is truly what's called an interaction with another variable, in this case the sex variable. It turns out that there are some drugs that blacks respond differently than whites. Maybe it's a race interaction. It could be an age interaction. It could be a lefties versus righties for some crazy reason if it's a psychological experiment. But how would you set up the experiment so you can test for a sex interaction here? Yes, Paul. You got to do it twice. I mean, there's no way to get around it. You got to test the men and women separately. Thank you, Paul. And basically, you got to set up the experiment. Now, hopefully, you got 9. Let's go back to the one-way thing. I mean, the completely randomized design. You have 9 males. These represent males. But then you got to set up the same experiment for. Again, it's 1, 2, and 3 is not correct anymore because there's really 9 people here. Each person is contributing one number. But now we got to do the same thing here for the females. And I'm going to make up numbers really quickly, like 8, 9, 6, and 3, 1, 1, and 2, 2, 3, something like that. So this picture represented the picture for the males. And now we're going to do the same picture for the females. So let's see, for the females, the average was 6, 8, and 9, I don't know, 7 point something probably. This is a picture for the females. The other than 3, 1, 1 is 4, 5, a little bit less than 2. So this is the thing for the females. And 2, 2, 3 is a little bit higher than 2, so it's here. So this represents the picture for the females. Make a double line. This is now the females. So before we just look at the male data, it's safe to say, as we said when we did the final F test, the drugs are not the same. First of all, we rejected H0. The drugs are not the same. And it turns out that this drug number 3 was really better than drug number 1 and drug number 2. We proved that by the Tukey-Kramer test, as the drug number 3 is better than 1 and 2. Well, can you say that? If you plugged all 18 numbers into the formula, do you think the computer is going to pop out and say drug number 3 is better? That's not a true statement. It's true for the males, but it's the opposite. Drug number 1 is better for the females. So the point is here, there is interaction between the drug variable, of which there are 3 possibilities, and the sex variable. So there'll be it's called a drug by sex interaction. A drug by sex interaction is the terminology you would use if you were doing this, more professionally. Now, So how do you prove that? Well, in this case, the way the book tries to get you to do, which I'm not going to make you do, is you plug the 18 numbers into some formula. It's very similar to the formula we